Hi. In this video, we are going to start our section on combinatorics. And the first topic that we'll look at is permutations and combinations. So we start off with the basic principles here, addition principle. So you might already be aware of addition principle. I will restate it. So if we have to accomplish some objective, and suppose the methods to accomplish some objective accomplish some task can be divided into n disjoint classes. Some tasks can be divided into n disjoint classes. And let's say there are m1 different methods to do the first class. And similarly there are m2 different methods to do the second class, and so on. M2 for the second class, and so on. Then the total number of ways of doing the whole task, total number of ways of doing the whole task will be simply m1 plus m2 and so on plus mn. So what does this mean? It means that if you have a set S, it's a finite set, and you want to count the number of elements in this set, and if you know that the set can be broken down into S1, S2, and Sn, which is a partition of S. What is a partition? Partition is a set of pairwise disjoint subsets. Pairwise disjoint subsets whose union becomes the whole set S. Pairwise disjoint subsets where S1 union S2 union Sn is equal to S. That is a partition of the set S. Then the number of elements in set S will simply be the sum of the number of elements in each of these subsets which form the whole partition. So this is basically your addition principle. This is only true if this is a partition of S and these sets are disjoint. If the sets S1, S2, Sn are not pairwise disjoint, then in order to count the total number of elements in the set S, you will have to do something more deeper, which is the principle of inclusion and exclusion, right? So we'll look at that in the later class. Right now, I just wanted to show you what addition principle is. Then there is multiplication principle. Multiplication principle is also pretty simple, and it says that if you have to do a task and the task can be divided into several stages, one task is divided into several stages, and you need to obviously finish all the stages in order to complete the task. And there are different number of ways to do each stage. Let's say m1 ways to do first stage, m2 ways to do second stage, and so on. Then the total number of ways of doing the whole task will be the product of the ways of doing each stage. So this is the total number of ways of doing the entire task, which was broken down into several stages. The logic here is that in order to complete the task, you must necessarily do all the stages, right? So you just have to multiply how many ways you can do each stage here. Okay. Then we come to the first concept of permutations. So permutation without repetitions. Without repetitions. So for permutations without repetitions, we are basically doing something like this. We are selecting and arranging k elements out of n different elements n different elements, and that is known as a k permutation. K permutation. And the number of ways to do it is n into n minus 1 in and so on till n minus k plus 1, which can be written as n factorial by n minus k factorial, and which is basically called npk. This is the number of ways of selecting and arranging k elements out of n different elements without repetition. Once you select a particular element, you cannot repeat that element, right? Suppose you were not selecting k elements out of n, but you were selecting all n elements, permutations of all n different elements taken all at a time, not k at a time. That becomes an n permutation basically, or a total permutation. And that would be basically, put k is equal to n in this equation, you will get n factorial by 0 factorial, which is simply n factorial. So that is your n permutation and a k permutation. Now we look at, excuse me, now you look at the next idea, which is basically permutations with repetitions. Permutations with repetitions. So the question is the same. We have to do a k permutation, but this time repetition is allowed. We have to select and arrange k things out of n different things, but with repetition. So this is pretty easy because we have to fill up and arrange k spots. Let's say these are k spots. The first spot can be taken in n ways, and now repetition is allowed. So the second spot also can be taken in n ways, and so on for all the spots. So this will simply be n power k, right? The next idea is full permutation of a finite number of repeated elements. So what is this? So let's say we have n elements that are divided into k groups, and elements in the same group are identical. In the same group are identical. So basically you can think of it as, like, suppose you have a few letters, right? So 2 A's, 2 C's, 3 D's, and 1 B, right? So the 2 A's are identical to each other, 2 C's are identical to each other, 3 D's are identical to each other. There are 4 different groups of letters here, and elements in the same group are identical. And let's say the number of elements in each group. Number of elements in each group is given by n1, n2, and so on till nk, because there are k groups. So the number of ways to arrange the full permutation of all n elements in this situation, number of ways to get the full permutation is n factorial by n1 factorial, n2 factorial, and so on till nk factorial. This is obvious because if all of them were different, you would have n factorial. But now since they are actually not different, you will have to divide by the number of permutations you have counted for here. So A has appeared 2 times. They are actually identical permutations, so you should divide by 2 factorial. 2 factorial is the number of ways to arrange AA if the A's were distinguishable from each other, right? So this is the full permutation of a finite number of elements which are repeated. And now from here, you should realize that this number is an integer. Since it is the number of ways to arrange these letters, it must be an integer. Now, if you take a special case here, n factorial by n1 factorial, n2 factorial, nk factorial is an integer. And now we'll take a special case. Let's say k was equal to 2 and n1 was equal to m and n2 was equal to n, right? So in that case, what you get is m plus n factorial by m factorial n factorial, which is equal to m plus n minus 1, and so on till n plus 1 by n factorial, by m factorial. This thing is also an integer, right? We are just taking a special case of the general formula. We are getting that this is an integer. How do I simplify this? I assume that you have cancelled out the n factorial. So all numbers below this, n, n minus 1 and so on have gotten cancelled. So what we are left with is m factorial in the denominator and the terms from n plus 1 to m plus n, right? Now notice this thing, since this is an integer, the top part, the numerator, is clearly product of n consecutive integers. Not n, I think it is the product of m consecutive integers. Why is it the product of m consecutive integers? Notice that it starts with n plus 1, then it is n plus 2, and so on. It goes on till n plus m, right? So it goes from 1 to m. So this is the product of m consecutive integers, and the denominator is m factorial. So this gives us a nice idea that always the product of m consecutive integers is divisible by m factorial. Is divisible by m factorial. This will come in handy later in problems. So that's why I'm making a point out of it. Let's move on. We go on to cyclic permutations. Cyclic permutations. So what is a cyclic permutation? We have to choose k elements out of n different elements, without repetition, followed by arranging them on a circle. So that this whole process of choosing k out of the n different elements without repetition and then arranging them on a circle is called a k-cyclic permutation. K-cyclic permutation of n different elements. So the number of ways to do this is to first select the nck. This selects k out of the n, and then arranging any element on a circle. N elements on a circle would be n minus 1 factorial. So this is nck into k minus 1 factorial, which can be written as n factorial by k factorial, n minus k factorial, and multiplied by k minus 1 factorial, which becomes basically n factorial by k into n minus k factorial, which can be written as npk 1 by k. 1 by k into npk. That becomes your result for the cyclic permutations. Now, here we were choosing k elements out of n. What happens if we choose all the n elements at a time? We don't choose just k. K basically equals n. In that case, you will see that this is clearly n minus 1 factorial. If you put n here, you will get npn by n factorial, which is n factorial by n, which is n minus 1 factorial, right? Okay, then we come to combinations, and the basic idea of combinations is simple. Combinations without repetition we are choosing k out of n different elements, and that can obviously be done in nck ways. which is n factorial by k factorial, n minus k factorial. On the other hand, if we have combinations with repetitions, so what this means is we have to take k out of n, but repetition is allowed. But with repetitions, that is equivalent to saying out of x1 plus x2 plus xn, these are the n things that are available to us. We have to select k out of them. That is equal to saying find the number of solutions of this function, right? Or this equation. Find the number of possible solutions of this equation. So solutions could be zero. Some of the variables could be zero also. So these are non-negative solutions, non-negative integer solutions of this equations. How did it become a equation problem suddenly? So the idea is that you have to decide how many of x1, you have to decide how many of each term are you going to take, right? So there are n different things out of which you have to pick some of them, but not the others, right? And you can pick multiple copies of one thing, right? So maybe you pick 2 times 1 and you pick 3 times 5 and so on. And that's how you selected the total number of k things, right? So we are basically now trying to solve this equation and finding how many solutions are there. So now there is a standard method, the stars and bars method, to find the number of non-negative integer solutions for this. I'm sure you must be aware of this. If not, there are other videos on my channel where I've explained this method. But the number of solutions here is simple. It is n plus k minus 1 ck. Number of non-negative solutions for this is n plus k minus 1 ck. Ck minus 1. No, actually it is correct. This is correct. Basically, you have n variables, so you need n minus 1 bars. You have k stars. So the total number of things is stars plus bars is n minus 1 plus k, c n minus 1, which is equal to this, n plus k minus 1 ck. So that is the number of ways to do combinations with repetitions. You have to select k out of n with repetitions. It becomes n plus k minus 1 ck ways, right? So now what we will do is we'll apply these ideas and problem solving methods in different questions. So I will show you a few examples that should help you process the information in this section. So first one is how many possible permutations can be made of 9 ones and 4 zeros. How many possible permutations can be made of 9 ones and 4 zeros if no 2 zeros are adjacent? No 2 zeros are adjacent. So when we talk about permutations, we have to arrange things and we have to count the number of possible arrangements. But the ones and zeros are identical to each other. So you have to be a little careful here. You have to also ensure that no 2 zeros are adjacent. The way to do such questions always, when no 2 things are supposed to be adjacent, is to arrange the other things first. Once you have arranged the other things, there will be gaps between them where you put the things which are supposed to be non-adjacent, right? So here, zeros cannot be adjacent. So let's put the 9 ones. These are 9 ones that I have arranged here. Since the ones are identical to each other, there is only one way to arrange them. one way to arrange them. And there are gaps here. You will realize that there are 10 gaps. 10 gaps between the 9 ones. You can place a 0 in any of these gaps. If you place a 0 in any of these gaps, no two zeros can ever be adjacent. How many ways are there of placing 4 zeros in these 10 gaps? There are 10 C4 ways to place zeros, right? One way to arrange 9 ones, 10 C4 ways to place zeros, and one way to arrange zeros. Because the zeros are identical, so there is no other way to arrange them, right? So the total answer is simply 10C4, which is 120. So that is pretty, not 120, actually it is 210. 10C4 is 210. And that was a pretty easy problem, but you have to get the idea of what can be arranged and what can't, and how to separate them out so that they are non-adjacent zeros, right? Let's look at the next problem. Find the number of 5-digit numbers such that each digit appears at least twice. Each digit appears at least twice. Okay, so we will do it in multiple cases. So first case is all 5 digits are identical. All 5 digits are identical. How many such numbers are possible? Obviously, there are only 9 such numbers. Numbers are of the form of this 1 1 1 1 1, 2 2 2 2 2, and so on, right? There are 9 such numbers. The second case is if the 5-digit number does not contain 0, doesn't contain 0, right? Then there must be 2 different digits, exactly 2 different digits. One appears twice and one appears thrice, right? If the 5-digit number does not contain 0, there must be 2 different digits. One appears twice and one appears thrice. Now, how do we find the number of total numbers like this? We can do 5C2 to select 2 of the 5 positions, multiplied by 9C1 to fill some digit into these positions, into these 2 positions. 9C1, because we can use any out of the 1 to 9 digits here. We have selected 2 positions. We have filled them in 9C1 or 9 ways. And then after that, we are left with 3 remaining positions and 8 remaining digits. So we can fill that in 8C1 ways or 8 ways, right? So 5C2 to select 2 positions where we put 9 ways to put an integer, and then 8C1 to fill the remaining 3 positions with another digit, right? Correct. So this gives us the total count. This becomes 720, right? Now we look at the third case, and the third case is basically the situation where if the 5-digit number contains 0, if the 5-digit number contains 0. So obviously 0 can't be our first digit, can't be our first digit. So we have 2 options. 0 appears twice. 0 appears twice. In that case, the first digit cannot be 0, right? So the first digit can be selected in 9C1 ways, right? Out of the remaining 9 numbers, 1 to 9, We can select the first digit in 9C1 ways, and after that, we can select where the 2 zeros will come out of the remaining 4. There are 4 spots remaining. First digit has been selected. Let's say 9. 4 spots remaining. You have to put zeros, 2 zeros here. So 4C2 ways to put zeros. Let's say here and here. And the remaining digits have to be 9. That is guaranteed. So there is nothing left to do. So this is simply 9C1 into 4C2, which is 54. And the second case is 0 appears thrice, right? If 0 appears thrice, we do the same thing. We fill the first space in 9C1 ways and then select 3 places where 0 will appear. The last place will be filled by the same digit as the first digit, right? So it will be 4C1, 4C3 into 9C1, which is 36. So the total number of ways is 9 plus 720 plus 54 plus 36, which is 819. So ultimately, you're getting 819 different numbers which will satisfy the conditions of the problem. Let's move on to the next one. The elements of a non-empty set. The elements of a non-empty set A are all positive integers and they satisfy this property. And they satisfy the property if small a belongs to capital A, or A is an element of the set, then 12 minus A also belongs to A. We have to determine the number of such sets. Determine the number of such sets. Think about it. The elements of the set are all positive integers. So they must be positive integers, and you have to realize that you can have 1, for example, then you'll have to have 11. This could be one set. Then you cannot have 13, however, because if 13 is there, then 12 minus 13 or minus 1 should be part of this set, but the elements of the set A are all positive integers, right? So any number n greater than 12 is not part of the set, right? So now basically you have to take numbers from 1 to 12 in such a way that you should never have a situation where one of the elements is there and the complement from 12 minus A is not there, right? So after you think about it a little bit, you should realize that A will simply be a union of these these 6 sets. A can be formed by the union of one or more several of these 6 sets. The 6 sets are 111, 210, 39, 48, 57, and just 6. A could be a combination union of one or more of these 6 sets. Why? You cannot have any other number other than this. You cannot put 0 because it's positive integers. You cannot put negative integers in it. You cannot have numbers above 12, right? Including 12, because of this reason we'll get negative integers then. So it must be a union of these sets, and also you must have, if you have 2, you must have 10. So this whole set must be part of it. Similarly, if you have 4, you must have 8, right? So it is clearly coming as a union of these sets. So how do we find the number of ways to select one or more of these sets? There are 6 such sets. So we can do 6C1 plus 6C2 plus 6C3 plus 6C4 plus 6C5 plus 6C6. We cannot select nothing. If you select nothing, then A is an empty set. So it has to be a non-empty set as mentioned in the problem. So you have to select one or more out of these 6 sets, and that basically becomes 2 power 6 minus 1 is equal to 63 waves. So basically, you will satisfy the conditions of the problem in 63 ways. Okay, let's move on to the next problem. Here we have this question. Take out A1, A2, A3 from the numbers 1, 2, 3 till 14 in ascending order from left to right such that A2 minus A1 is always greater than 3 and A3 minus A2 is always greater than equal to 3. Find the number of ways to meet these requirements. Find the number of ways to meet these conditions. Okay. So we have to pick out 3 numbers from the set 1 to 14 and in ascending order from left to right. So you will always have A1 is less than equal to A2 is less than equal to A3. That is the situation in which you are picking the numbers. Now, if the restriction was not there, obviously you could have picked any 3 numbers out of the set of 14 numbers and you would have said 14C3 and then you could have rearranged them in ascending order and said the lowest one is A1, the middle one is A2 and the highest one is A3, right? And that would have been fine. But the problem here is that there is this restriction, right? You have to ensure that the gap between A1 and A2 is at least 3 or more. And the gap between A3 and A2 is also at least 3 or more, right? So that is why you cannot do 14C3 ways. This becomes wrong. You cannot arbitrarily select 3 numbers because then they might not have such a big gap, right? So what we'll do is we'll analyze these 2 conditions and understand how many actual options do we have of selecting numbers, right? So we will say that A2 is greater than 3 plus A1. Therefore, that means A2 is strictly greater than 2 plus A1, right? A2 could be equal to 3 plus A1. So A2 is strictly greater than 2 plus A1. So we have A2 minus 2 is greater than A1, right? And similarly, A3 is greater than or equal to 3 plus A2, which means A3 is strictly greater than 2 plus A2, or you have A3 minus 2 is greater than A2, right? These 2 conditions we have. So therefore, we can say that A3 minus 2 is greater than A2. So now we write A3 minus 4 is greater than A2 minus 2 and A2 minus 2 is greater than A1, right? So we have these 3 conditions, which is a strict inequality. So if you call these numbers as B1, B2 and B3, right? B1, B2 and B3, they are satisfying this strict inequality, right? Now think about it. What is the highest number that A3 can be? A3 could have been anything from 1 to 14. So A3 could have been 14. So A3 minus 4, which we are calling as B1, can be 10, right? If A3 could have been 14, B1 could have been 10, right? And after that, anything less, the smallest number here is what? A1 could have been 1, and then B3 could have been 1, right? So basically, you are selecting these 3 numbers, A3 minus 4, A2 minus 2, and A1, which we are calling as B1, B2, B3, from the set of numbers 1 to 10, right? If you make sure that B1, B2, B3 is from 1 to 10, you will always have A3, A2 and A1 satisfying these conditions, right? So what we are saying is that we can select A1, A2 minus 2 and A3 minus 4 from the set 1 to 10 without any restrictions. Why 1 to 10? Because the highest value of A3 minus 4 can be 10 and the lowest value of A1 can be 1, right? This is without any restrictions. There is no issue now because these are non they don't have to be equal. There's a strict inequality between them. So the number of ways is simply 10C3 here. How many ways to select three numbers from the set 1 to 10? It's simply 10C3. So that is the answer. Keep in mind this problem. This problem comes in very handy many times. This is like you are going from one station to another station and there are multiple stations in the middle where you can stop, the train can stop. And the gap between the stations must be greater than 2 or greater than 3 or whatever. So this type of problem has been framed before in different contexts. So try to go through the solution again and make sure that you understand it properly. Let's move on to the next one. Question 5. The question is how many subsets of 1, 2 till 100 contain at least one odd number? At least one odd number. Now, this will introduce a very important technique of complementary counting. Basically, it is difficult to count directly this question because at least one odd number, you could have one or more odd numbers, right? So there will be many cases of having different amounts of odd numbers, right? So the best way to do it is to subtract from the total number of subsets. Total number of subsets is 2 per 100, and we can also say that number of undesired subsets which have zero odd numbers in them is equal to subsets of the set of even numbers 2, 4, 6, 8 till 100, right? The subsets of this big set, the set of all the even numbers in the universal set, will be the undesired subsets, right? We don't want these subsets because they don't have any odd numbers. And the subsets of this will be 2 per 50. So the actual answer by complementary counting is 2 per 100 minus 2 per 50. That becomes our answer. So this is a very simple application of complementary counting. You should be aware of this technique, right? Let's look at the next problem. Suppose each term of a sequence, A1, A2, AN is one of 0, 1, 2 till k minus 1. Here k is greater than or equal to 2 is an integer. Find the number of sequences. Find the number of sequences in which 0 appears even number of times. 0 appears an even number of times. We have to find all the sequences where 0 appears even number of times. And each term of this n term sequence can be anything from 0 to k minus 1. So we will say let x of n and y of n be the number of sequences where 0 appears even times and odd times. Even times and odd times respectively. Okay. So for each integer I, let's say there are I zeros in a sequence. I zeros in a sequence. How many such sequences are possible? How do we count the number of sequences which have exactly I zeros, right? So you have to select which positions out of the n you will place the I zeros, right? So you will say NCI, that is selecting where to place the I zeros. Once you have placed the I zeros, you have to think about what happens to the rest of the n minus I spots, right? Actually, there are n minus I other spots available, and there are k minus 1 choices for numbers in each spot, right? You can pick 1, 2 till k minus 1. There are k minus 1 choices for each spot, and there are n minus 1 spots available, and you can repeat numbers, so it will be NCI multiplied by k minus 1 power n minus I, right? This is the number of sequences containing exactly I zeros, right? I hope you understood this logic here. Now, if you want to count the number of sequences where 0 appears even times, we just generalize this idea here and we say xn should be equal to the first case when 0 appears 0 times, nc0 k minus 1 power n minus 0. Then 0 appears twice, nc2 k minus 1 power n minus 2, and so on, nc4 k minus 1 power n minus 4. This is the way you construct xn, right? And yn, when it appears odd number of times, would be nc1 k minus 1 power n minus 1 plus nc3 k minus 1 power n minus 3, and so on, right? That will be yn. Now it is very easy to find xn here because we know xn plus yn by binomial theorem is simply 1 plus k minus 1 whole power n, which is simply k power n. And you can also show that xn minus yn is equal to 1 minus k minus 1 power n, which is k minus 2 power n. Actually 2 minus k power n, but we'll write it as minus 1 power n k minus 2 power n, right? Depends on whether n is odd or even, right? Correct. And once we have xn and yn, we can just add and divide. So xn will be equal to half of k plus n, k power n plus minus 1 power n, k minus 2 power n. So by applying binomial theorem, you can recognize that the sum of this and the difference of this is fitting the pattern of binomial theorem expansions, and that helps us solve the problem, right? Okay. One last question. Let's look at this one. We are saying take out any three different numbers from 1 to 300, 1 to 300, such that the sum of the three numbers, the sum of the three numbers is divisible by 3. How many options are there to take out these three numbers? How many ways are there to do this? So what you have to think of is when you take out numbers, you can take out numbers of the form 3k, which is from 0, not 0, which is from 3, 6 till 300. You can take out numbers of the form 3k plus 1, which is 1, 4 till 298. Or you can take out numbers from the set 3k plus 2, which is 2, 5 till 299, right? Now there are four different cases in which you could have the sum of the three numbers that you taken out is divisible by 3. So the three cases are all three numbers belongs to one set, either A or B or C. All three numbers, if they belong to one particular set, the sum of the numbers will always be divisible by 3. You can check that. And if all three are from one set, you can say 100C3, 100C3 if they are from set A, plus 100C3 if they are from set B, plus 100C3 if they are from set C. So basically you get 3 times 100C3 for the first three cases. And the fourth case is when one number from each set is taken. One number from each set A, B, and C is taken. Then also the total sum is divisible by 3. So in that way, the number of ways is 100 power 3 for you. Because to take one number from the set is 100 ways, and you have 100 into 100 into 100. So the overall total number of options available for you would be the sum of 3 times 100C3 plus 100Q. That should be your answer, right? So we have looked at fairly simple problems of permutations and combinations so far. We'll get to harder problems in combinatorics soon, but keep in mind the models by which we are solving the problems here and the basic theory is absolutely essential. And we'll keep using these concepts in the next few videos and the next few topics in this section as well. So hopefully you learned something from this video, and I'll see you next time.